Hi, I'm Vineet Ganju from Synaptics, and I'm joined by Gene Rice from Eta Compute. Together, we're going to introduce you to the Katana low-power AI platform and Tensai AI compiler tools. Katana is an exciting new low-power Edge AI processor, and together with the Tensai tools, enables on-device AI inferencing in battery-powered or low-power AI applications. The Tensai tools enables AI developers to develop, port, and optimize AI models for the Katana processor. Now Gene will run through a demo of the tools.
Our person detection model was built and tested with this workflow. The model is retrained with selected person-no-person images that are resized and converted to grayscale. The TensorFlow model is then quantized and converted to TensorFlow Lite. The model is run on a workstation or compiled by tensaicc for an embedded neural processor such as the 3532 or Synaptics' new Katana chip. tensaicc compiles the TF Lite file into C source code. Next, I will demonstrate the tensaicc compiler and then show workstation testing. Next, we'll compile the TF Lite model to C and build the embedded executable. The tensaicc compiler takes person detection.tflite as the input model. The output is to the current directory, and the weights will be calculated and stored in the include directory. The output of the compiler is 206,000 8-bit weights, and it's going to require 54K RAM to run this model. The output of the compiler is infer.c, which is the C equivalent of the TF Lite model. Also kernel config, which directs the build system to include certain neural network kernels. We're going to move that up a directory so the build system can find it. Next, we're going to make the build directory again. To make sure there aren't any leftovers from the previous build. We use the CMake system to build all the make files we need for the project. And we're loading most of the configurations automatically. We need to add a couple of configurations by hand here. I'm switching from the evaluation board to the AI vision board. And enabling UART1. Saving the configuration. Okay, the configurations are done. We're going to make. Now the build system is compiling infer.c along with the TensorFlow middleware and generating a binary file. Okay, that has built successfully. Now we'll erase the board. And we'll flash that image into the board. Next, we'll run PuTTY to look at the output. And reset the board. And we have a person detected. Let's look at how the TensorFlow Lite model is tested on a workstation. These are the files used in the test. Bench.bat is the script that starts the test with the selected parameters. Benchmark is the Python program that contains the test code. Person detection.tflite is the model that we're testing. And labels.csv is a file that lists all of the images and whether or not there's a person in that image. Here's some examples of those images. These are the modules that are required by Python. Let's run the benchmark. The benchmark has 4 parameters. We're running the workstation version. This is the input directory. This is the model that we're testing, and this is the output directory. This is going to take a few moments, so let's pause here. The results give an accuracy of 82%. We have a confusion matrix, detailed metrics, and the ROC curve. Let's look at these in detail. Here's the confusion matrix. It is mostly true positive and true negative, as expected, with a few false predictions. The metrics file shows detailed metrics such as precision, recall, F1 score, and support. The predictions file shows the results for each of the individual images. This shows the name of the file, it shows whether there's a person or not, and then it shows whether a person is predicted or not. The scores for unknown category, person, and not person are shown. Here is the ROC curve. This has an area of 91%. And finally, let's look at the results of the workstation accuracy versus the neural sensor processor. The accuracy of the workstation is less than 1% better than the neural sensor processor. Both the chip and the workstation start with the same 8-bit weights. The workstation is slightly more accurate because its intermediate computations accumulate residual results that trend towards more accuracy by the end of the calculation. This demo shows the neural processors can be effective for low-power applications and cost savings.